Thanks, Will. Thanks a lot for very nice talk, uh, illuminating. So let's take some questions from the audience. So you can just unmute your mic and ask.
Let me show one more picture while we're waiting for questions.
Please, please.
This transition from striation to flocculation is actually something that you have seen before.
Yes.
This is from a DuPont plant in Newark, Delaware, and you can see the dynamics. You have here's your magnetic flux tube in the bottom, constraining the flow, and as you see, you have striated flow immediately when it exits, and it makes a nice transition to flocculated flow later. So what the idea that we're describing is not so unprecedented.
Indeed. So let me ask some questions. Start with one. So you are kind of saying that there's an instability near 30 solar radius or 35 solar radius. So
well, yeah.
So Reynolds number is reasonably high. So instability would have occurred before 35 solar radii, or I'm kind of not getting that picture. You understand my question? I mean, supposedly it's like a pretty fast wind in the solar corona. So could you just illuminate on that part?
Well, in fact, our colleague Melvin Goldstein pointed out to us while we were writing this paper, the Ruffalo paper, that there actually some evidence very deep in the corona that in certain places the magnetic field does appear to reverse, almost down at the transition region. So this is not an absolute where there's absolutely no roll-ups at all on the left side, but I think we think that there's a great increase in the likelihood of roll-ups outside because the prevailing parameters favor it out here. But lower than this, to get the right parameters would be an extreme event, let's say.
I see.
Something very much less likely. But it's not absolutely prohibited.
Okay.
You could have places where the Alfven speed becomes very low, for example.
I see.
And of course, in the chromosphere, which is the very thin layer right above the photosphere, this thing happens constantly. There are shocks and reversals and everything, but it's just that above the transition region where the temperature goes up by a lot and the density drops a lot and the plasma beta drops very suddenly. I mean, in over a distance of like 1,000 kilometers or something like that, there's these orders of magnitude changes in the plasma parameters. And after you pass that, the magnetic field really becomes the guiding constraint. Not absolute, but almost absolute, I would say. And you can see that in the pictures, right? I mean, if you go back to this picture, it's very clear that in most of the places, the plasma is highly constrained, which does not mean it's in equilibrium. There's component reconnection going on in here and coronal mass ejections and things. But I think really the picture, they say a picture is worth 1,000 words, right? You can see that the plasma is constrained mostly.
Okay. So I mean, I think I'll just make one comment or question in some sense. So there is a small scale turbulence which may be at a very small scales, or very small means in the framework of solar wind, where Kolmogorov or some power law or some turbulence at small scales, but these instabilities that Kelvin-Helmholtz or shear instability occur for large scale flows, because in the solar surface.
Yes. Okay. That's true. There's turbulence everywhere in this picture.
Right.
Nowhere is it in equilibrium. And I would claim, even though it hasn't been measured, I would claim that there's turbulence everywhere. But the turbulence deep in the corona is going to be highly anisotropic. And to a reversal of the magnetic field, you need a pretty large parallel wave number perturbation. Right? I mean, most of the perturbations here are in the transverse directions across the flux tubes. So what that means is, if you like, in any of these pictures, in this picture, I drew these tubes too smooth. They're not this smooth. Actually, there's component reconnection, there's waves traveling along, but the turbulence down here is very anisotropic with mostly K vectors perpendicular to the mean field. There's current sheets in between the flux tubes. There's probably current sheets inside the flux tubes, kind of like the critical surfaces, singular surfaces in a tokamak or a reversed field pinch. And you can have dynamics there. You can have internal reconnections, but it's going to be very hard to reverse this magnetic field without something very powerful occurring.
Indeed. Yeah. I mean, I agree with that. This large scale picture is a much better way to explain that reversal of the magnetic field. And
I mean, these are really large 200 kilometer per second velocity differential is a large perturbation. The question is, can you tap that energy? And by triggering Kelvin-Helmholtz, you can tap that energy reservoir.
That's right, precisely. Okay, some other questions, please.
Hi, Bill. This is Rajesh, and I have a question.
Okay,
so
Rajesh.
First of all, it's a very interesting talk, and I come from hydrodynamic background. So the magnetic thing is something new, but we also observe that when we increase the compressibility, the flow becomes more stabilized compared to if the Mach number is very, very low. So from that perspective, my question is like, you said that because of the magnetic field, the KH instability becomes more and more unstable, and you really need a high ratio of the velocities to get this KH kind of instability. Right.
Yes.
So when go ahead, please.
No, I was just going to say that I think even laboratory experimenters know this from that you can suppress turbulence to some degree with magnetic fields. But of course, if the shear is strong enough, you can't do it.
Sure. So when there's a direction and the reversal of the direction of the magnetic field, does it amplify the instability, or it has no effect?
Which thing did you say?
So you said that there's a reversal of the magnetic field, right, due to this KH roll-up, right? So suppose we use that magnetic field instead of the forward direction magnetic field. Will it not amplify the KH stability, or it will always destabilize the stability, regardless of the direction of the magnetic field?
I think that in this fully developed state, to the right hand side of the movie that I showed, or the later times in the other movie, the magnetic field is a full participant in the turbulence at that point. I mean, there's a magnetic field energy cascade. In fact, the correct variables to look at it, even if it's incompressible, are these Alsacer variables, which are the sum and differences of the velocity and magnetic field. And the velocity plus magnetic field interacts with velocity minus magnetic field as kind of virtual fields. And these wave packets can actually collide and produce the cascade. You're probably familiar with the Kolmogorov 4/5 law, the third order law for the cascade rate. In MHD, incompressible MHD, there's a third order law that involves the mixed third order correlation involving, say, 1 power of the plus Alsacer variable and the square of the second one of the negative Alsacer variable. So you need to have both. You need to have both kinds of fluctuations to get turbulence. But if you do, the magnetic field is a full participant at that point. The thing that really suppresses the turbulence is, of course, if you have no velocity field, then it's hard to have turbulence. But also if you have velocity and magnetic field that are everywhere parallel to each other, that tends to suppress the turbulence, just as it does in the cartoon. You have velocity and magnetic field parallel to each other. But even if the magnetic field were curved, if you have high, they call it crossalicity or alphanicity. If you have high alphanicity, that turns off the nonlinear terms in the equations. So it's actually kind of messy because there's different regimes where there's more turbulence and other regimes where there's less. But you certainly can have turbulence even if the magnetic field is very highly distorted.
Okay. Yeah, thank you very much.
Oh, sure. I don't know if I answered your question, but you can
Yeah,
email me. If you
sure.
have more questions, please email me.
Sure. Thank you.
I have a question.
Yes.
Please.
Yeah, thanks, Bill, for a very nice talk. This is Abhishek from IIT Bombay. I was thinking about the connections that you were trying to make, or maybe you mentioned between the reconnections and switchbacks. So reconnections, from my knowledge, they are typically quite fast. They have short time scales. Whereas this switchback seems to be quite stable because they have been found by these probes which are quite far. So in that sense, does it not look a little bit strange to connect these two things?
I absolutely agree with you, Abhishek. That's one of the reasons why we think the model we're talking about is more viable, because if you reconnect near the solar surface, almost certainly something is going to happen to destroy the pattern of the switchback. I mean, it might pump turbulence, but it's not going to give you a coherent switching back process. And as I said, Anna Tenerani at Texas and Austin has simulated this in MHD codes, and she actually estimates the rate at which the switched back field from interchange reconnection will decay away. I mean, she doesn't think that very many of them will make it. So there's an interesting question, right? If the switchback, if the interchange people are correct, that their model is the main source of these, which I personally doubt, and apparently you do too. But if they're right, then as you go deeper and deeper into the corona in subsequent orbits of Parker, you should see more and more switchbacks.
Yeah.
Whereas if we are correct, you should actually see less and less switchbacks, because eventually you're going to get near this source, this critical region below which there shouldn't be any switchbacks, or extremely rare switchbacks. Right. So we think we're out here somewhere where they're pretty common, and they should get less and less common, and they should go away. But if the interchange people are right, there should be a lot more under the critical surface. So we'll find out.
Yeah, we'll find out. Thank you.
Physics is an experimental subject, right? I mean, and there's two hypotheses, and there's going to be a clear answer. And I think we're probably right, but I'm not 100% sure till we have the evidence, right?
Very, very fascinating. Thank you.
Yeah, thank you.
Okay, so connected to this, I have one question. So instability has a wavelength, no? There's Kelvin-Helmholtz. I don't know about with magnetic field. Chandrasekhar's paper, book I have not read about MHD including, but Kelvin-Helmholtz without magnetic field has a wavelength. I don't know, KH is so.
The wavelength is some multiple of the thickness of the vortex layer. Yeah, something like that, right?
So that prediction matches with observation,
that would be like the expected wavelength or wave vector of the fastest growing mode.
Right.
The problem here is that this is not starting from an equilibrium plus a infinitesimal perturbation. The perturbations, the pre-existing waves are inside these flux tubes are probably pretty large.
I see.
So now they might have a preferred wavelength, and that might swamp the fastest growing linear instability. So I think it's probably a mistake to assume that this is going to obey linear theory.
Okay.
Because it's simply not an equilibrium.
Great. Okay.
It's more like turbulent flow in a pipe, and then the pipe ends.
Okay.
So it's not exactly that either, but anyway, because it's highly anisotropic. But I wouldn't expect to see a single fastest growing mode.
Yes. It makes sense. Okay, great. So I think
not everybody agrees with me about that, by the way.
Really, I see. Okay.
You mean to say the flow is saturated already?
Sorry?
You mean to say the flow is saturated already, so the linear theory will not be applicable there?
Yeah, you already have a Kolmogorov spectrum there. So why should you see the fastest growing mode from a linear instability? It's an anisotropic Kolmogorov spectrum, but that's going to give you a broadband perturbations once this process is unleashed out here. I see Sean Alton.
Yes. Hello, everyone. Thanks for organising this, Mahindra. It's great. So two things. First, a comment on what you're saying there about this distinction between the linear instability stuff versus this instability here, which is really quite different. It's almost like we need a better word, because if you say instability, then everyone thinks linear instability.
Yeah.
And we can say non-linear instability, but people still think, oh, yeah, you've just gone a little bit further.
Yeah.
I don't know what that word should be, but
yeah, no, I agree that there's a vocabulary problem. I mean, for my PhD thesis problem, I did two-dimensional reconnection problem, sheet pinch simulations, and I started them with broadband finite amplitude fluctuations, and I asked the question: how small do the perturbations have to be before you see linear tearing? And you do see it, but you have to go to extremely small levels of perturbations if the perturbations are broadband. If you put a single mode in or a few modes, then you can more easily pull out the linear theory. But I was putting in a power law spectrum at a low level. And under those circumstances, it's very hard to see any reasonably long period of time in which linear theory remains accurate.
Right. Analogous to the Ewell-Sommerfeld stuff in the pipe flow, I guess.
Yeah. Yeah, I mean, you can actually you can sort of see it in this simulation of the hydrodynamic case. Where is it? Oh, it's in the other direction. Yeah, I mean, in this case, I guess the plate ends right here, and you can there might be some region here where you're seeing the fastest growing mode emerging, but by the time it starts rolling up, it clearly is very broadband. I mean, there's not even a fixed parallel mode number there. Sometimes they're bunched up and sometimes they're not. Maybe back here when the perturbations are too small to see, maybe linear theory. What is that? It's an Orr-Sommerfeld problem, right?
Yeah.
By the way, one more comment connected to Sean's comment, that maybe you can call it large scale instability or something, so that the small scale is turbulent, but by the way, in Earth also they see this, there are wind patterns which becomes unstable by Rossby waves or something. So that is generic phenomena. Large scales are affected by large scale forcing and instabilities. You see my point, Bill? What I'm saying? The Coriolis force supposedly does something to the oceanic currents and.
Yeah, well, but isn't it? I mean, I'm not an expert in ocean turbulence, but I think in that case there are strong large-scale instabilities, right?
Precisely. So there is turbulence as well as instability. That is what I mean to say. Yeah. And that's what you have it here.
Oh, absolutely. I'm not saying that there's no such thing as a linear instability. I just don't think that this problem is tractable from the point of view of linear theory.
Indeed. So we don't need a linear theory, but we need to have description that large scale instability occurs, which is coupled with turbulence at smaller scales. So I think that is the framework. Great.
In space physics, we sometimes use macro instability as opposed to the micro instability, which is like due to the kinetic processes.
I see. Okay, great. Yeah,
Hi, Bill. Am I?
Yes.
Hi, Supertic.
Yeah.
Are you there?
Hi, Bill.
Hi.
Yeah. So I have a small question. Yeah. So I have a small question. So in general, just correct me if I am wrong. So in case of traditional Kelvin-Helmholtz instability, we start with the assumption that the fluid is fairly incompressible and the initial vorticity is negligibly small. Now, incompressible, I don't have much problem, but how can we justify the problem that the initial vorticity is negligibly small so that you can actually write some scalar potential for the velocity field? So do we like that?
No, maybe I should be saying Rayleigh-Taylor instead of Kelvin-Helmholtz. But no, I don't think this is Mach number 3 or something like that. I don't think that this, even though the density fluctuations are small, I don't think that a incompressible framework is the correct framework to describe this dynamic.
That is also true. That's also true. That's also true. That I agree. Yeah. That I also, I mean, but the question is that the theoretical formulation for compressible Kelvin-Helmholtz or vortical fluids, are they done really? I mean, because in the normal literature, we cannot see, right? I mean, for example, in Chandrasekhar's work or something.
Well, in the Chandrasekhar book, he does the compressible calculation.
It's a nearly compressible, right? I don't know. For the high Mach 3, I am not sure, but anyways, yeah.
Yeah, I'm not. I'd have to go back and check whether he went to very high Mach numbers.
Yeah, okay.
But for sure, this is a slightly, for me at least, an unusual parameter range to look at turbulence, where you have Mach numbers, sonic Mach numbers greatly exceeding 1. But it's also quite Alfvenic, and the velocity and magnetic field are so aligned. So I think it needs to be explored, maybe analytically and in more simulations.
Yeah. Of course.
For example, these like rarefaction shocks that we see coming off the corners. There's actually a section in Landau and Lifshitz's fluid mechanics that talks about flow around a corner.
Okay.
And it looks very intriguing that there might be actually the same kind of rarefactions he talks about in flow around a corner might be occurring when the streamlines, the flow tries to go around one of these roll-ups, and then you get this rarefaction, and it's very much of a straight line coming out. And when in the Landau and Lifshitz calculations, there are defects in the solutions where that flow along lines. It's very much looks the same, and we have to explore that more.
Okay.
I think there's some interesting work to do there.
Yeah.
So,
I am just thinking about that exactly. Yeah. Okay. Yeah.
I mean, you of all people know very well that the compressible case is very interesting.
Yes, of course. I mean, complex as well, huh?
Complex, yeah, absolutely, absolutely.
But thanks for the wonderful talk. This is a totally different subject. I mean, from the traditional solar wind problems, this is a totally different thing. I mean, really, we have to explore.
Yeah, I think there's a lot to look at. Yeah, and I like the fact that this subject looks like an elaboration on fluid mechanics when you think about it. I mean, and I think that solar wind physics can definitely use more fluid mechanics people looking into the dynamical processes.
That's our
space plasma people these days just want to talk about reconnection. They really don't want to hear anything else.
That's true. No, I agree. More fluid.
I'm exaggerating a little.
But more fluid should be in. Thank you very much. Thanks a lot.
Yeah, no, I think so. So I'm glad if there's some fluid mechanics people listening.
Okay. Yeah.
Read about solar wind and write papers on solar wind from a fluid mechanics perspective.
Fluid mechanics perspective, right. Yeah.
Please do this. Yes.
If the community does not reject in a moment, that's the only thing we are always afraid of. Well, we will see.
Well, if you say you think they'll reject your papers if you do them that way, you ask for me as a referee.
Thank you very much. Okay, thanks.
Okay,
thank you for
great. Okay, so thanks, Bill, again. Thanks to you for the nice talk and for getting us together.
Okay. And thank you very much for inviting me, and thanks to all of you for attending. Nice to see some familiar faces on here too.
Excellent. Okay.
So
bye. So
namaste.
Have a good day and have a good night and have a good sleep, some of you. Okay. All right. Okay. Bye.
I'll sign off then. Thanks, Mahendra.
Thanks, Bill. Thank you. Thanks to all of you.
Talk to you soon, Sean.
Yeah. Good to talk to everyone. See you soon.
Yeah. Bye-bye.